Hi, we're Team Think Outside the Rat Box. I'm Leah.
I'm Katie.
I'm John Blake.
I'm Brittany.
As a brief reminder, the goal of our team's project is to assemble and program an indirect calorimetry device that can be placed on top of a standard rat cage in order to assist with diabetes and obesity research in partnership with the Herman Van Horn Research Lab at ASU. Since the last video, we have troubleshooted all issues and completed all internal testing to validate our device. Each team member has contributed based on their strengths, and together we have completed a functional indirect calorimetry device. In the final stage of the build, wiring the devices was a crucial component. The wiring was split into two parts, the power circuit and sensor connections. For the power circuit, the carbon dioxide and oxygen sensors require different input voltage levels, so an AC to DC power supply converter was used in accompaniment with a buck converter to meet sensor specifications. For the sensor connections, the wires are threaded through 4 separate holes in the sensor boxes, and each sensor has one hole for sensor readings connected to the Arduino and one for power and ground connections. The holes were then hot glued into place upon completion of the device wiring to create an airtight seal around the box.
During the second half of the semester, I finalized our device program. Written in Python, the program gets readings from all 4 sensors, processes the raw data to calculate EE and RQ, and outputs values in a .csv file as requested by the Herman Van Horn lab. A large chunk of time was also spent developing a graphic user interface, or GUI, to make running experiments with the device as easy as possible for researchers. The GUI breaks the experiment into 3 easy steps: user input, sensor calibration, and running the experiment. The GUI validates user input, shows the user how much time is left in each step, and updates to show the most recent readings from the sensors. The program and device were tested together in multiple experiments ranging from 30 minutes to 24 hours, which demonstrated the accuracy of the sensors and the ability of the device to run for day-long experiments as required by the Herman Van Horn lab.
One highlight during the second half of this last semester was that we met with another research professor at ASU to provide a safety demonstration to obtain IACUC approval to begin testing on live animals. This presentation was a success and we received the approval we needed. The next step for the lab is to obtain rats so that live animal testing can begin. Beyond this, I continued to work on 3D printing structures. One concern of our design was that the loose wires were prone to accidental disconnection. To remedy this, I printed a frame that holds a thin sheet of plexiglass over the power circuit on Arduinos to protect the wires during an experiment.
In the final stretch of the semester, I have worked extensively with the documentation of the indirect calorimetry device. Because we are working for a biology lab with little technical engineering background, we want to make sure to leave thorough instruction for how to operate the device to set the lab up for success when we graduate. This has included logging the physical build, the circuitry and hardware, and the program. The instructions were compiled and neatly organized in one user manual document. Ultimately, the team was able to successfully implement gas sensors, microcontrollers, 3D printed designs, and a Python program to calculate rodent respiratory activity. The device met all customer requirements and has been approved for animal testing by IACUC. Overall, the design costs approximately $650 to assemble, which is more than 5 times cheaper than devices sold by industry. The team's cost-effective approach was a success, and we are excited to see it implemented in real animal research.